In this lecture, we're going to quickly touch on formal charge. So this is another topic from, or really Organic Chemistry 1. It's crucial to really understanding organic reactions. But like I said, it's been a while. So this is sort of a warm-up lecture. I'll be super quick. There's a lot of resources out there, but just maybe seeing the formula again will help spark your memory, jog your memory a bit. So warm-up lecture number 2, I guess. We have formal charge. And so we have this equation, which I'll just label formal charge as Fc. That's equal to the atom group number for the atom of interest. Remember, formal charge is the charge of an atom within a molecule. Perhaps I should define that. So it's the atom group number minus the number of bonds to that atom minus the number of, sorry, I'm running out of room here, unshared electrons. Okay. So that equation is particularly useful to have at your fingertips, but just in general, if you look at many of these over time, you'll just sort of accidentally memorize what the formal charge is of these atoms in their particular states. So for example, just sp3 carbon with 4 different things attached to it. We could look at the formal charge of any of these atoms, but carbon is particularly interesting to us. So we start with the atom group number. Carbon is element number 4, even though it has, a larger atomic mass. That's not what we're looking at. We're looking at that group number in the periodic table, which is 4. It's also equal to its valence minus the number of bonds. There are 4 lines to carbon. It has 0 unshared or lone pair or non-bonding electrons. And so 4 minus 4 equals 0. The formal charge is then equal to 0. And we could put a little 0 over this, but nobody does that. If there's no charge, we just don't label it with anything. Now, let's use this equation in a more complicated setting. So before we had mentioned Dmso, a really important solvent in chemistry and in many industries. And so Dmso is dimethyl sulfoxide. And it has an unusual structure in that you, in many cases, want to draw this molecule like this. But when you see the lone pair of electrons on the sulfur atom, which some people often forget, so let's see, if I just delete those, this looks like a better structure because everything has an octet, seemingly, but sulfur has a lone pair of electrons down here, which is critical to getting its formal charge right and to just really understanding its electronics well. But so this molecule is has expanded its octet because we're no longer in row 2 of the periodic table. So what we can do is we can look at the formal charge in various positions. Let's pick on the oxygen. The oxygen is a group 6 element. It has 2 bonds to it, and it has 4 dots surrounding it, or 4 non-bonding electrons. Remember, we don't count the lone pairs as 1, we count them as 2 because there are 2 unshared electrons in that system. We have a formal charge of 0. Now, sulfur is actually in the same group of the periodic table as carbon, so it's also group number 6. It has 4 lines to it, and it has 2 bonds, or excuse me, 2 unshared electrons. You see what happens if you forget those, that lone pair of electrons, those unshared electrons, is that you will get the formal charge wrong. So in this case, the formal charge is 0 and 0. Now, this is one way to depict the molecule, but an alternative way is to draw the resonance structure. The resonance structure of this, remember, is a different way of drawing how the electrons are arranged, particularly those as lone pairs and pi bonds. And so what we could do is, instead of having 2 bonds to sulfur, we could have, between oxygen and sulfur, we could have 1 bond where we push the electrons up and onto the oxygen atom. When we do that, that formal charge now changes in the case of both molecules, where we have, for oxygen, we have a group 6 element still. We now have 1 bond, and we have 6 unshared electrons, giving us a -1 charge. Now, for sulfur, we have a group 6 element minus 3 bonds minus 2 electrons is equal to +1. So here we would label a plus or a +1, a -1, or just a minus for the oxygen atom. Now, what I want you to note is that the overall charge on the molecule is 0 for both of these depictions. So I'm going to write overall neutral and overall neutral. Now, what I've done in depicting DMSO in these two different ways is just shown two different representations of the molecule where we've changed how the electrons are formally depicted within the molecule. Now, what we've done is just shown two possible ways to sort of think about where the electrons are. Now, what's the true structure of DMSO? It's some sort of average of these two structures. So they're both kind of right in their own way. And we're going to look at that in more detail for the next video. So these are, if you don't remember these are resonance structures. Different bond line depictions of a molecule where the electrons that exist in pi systems and those double bonds have sort of moved. So I know we've all heard this term before. Maybe it's been a while since you've thought about it, and that's what we're going to look at in the next video. So that's it for now.